Okay, we're back. Let's see what you can do with your students that relates to this concept of the B-pillar and designing for minimum mass. So to turn this B-pillar design into an actual lab that would work in a classroom, we had to make some simplifying assumptions. So we've come up with some ways for you to create an impact test using either a fixed impact energy or variable. So we'll be describing those at the end of the presentation. One of the things that we had to really simplify was in the real test, your B-pillar is attached to your roof and your floor. That makes the math really hard. You need calculus instead of our simple algebra. And it's really difficult for your students to construct something like that. So we're going to test our beams where we're either holding one end or letting both ends move freely. And as we noted, the B-pillar is a complicated assembly with hollow parts for the seatbelt, door latches, and all kinds of other features. So we're going to simplify this to a rectangular shape, okay? And we're going to stick to one beam length. So most of our beams in our labs are going to be tested in cantilever bending or in three-point bending. So in cantilever bending, I'm just going to grab a hold of one end of the beam, and I'm going to somehow apply a force to the other end, and I'm going to measure the relationship between force and deflection. Okay. The other way to do this is to support the beam on both ends. So I'm going to place this on something that will raise it up, and then I can either hang a water bottle from the middle of it and add weight, or I can stack mass on top. So our testing scheme is pretty simple. So as I mentioned, we created 4 experiments. The first one looks at shape effects. The second one looks at material effects. And those probably both take 1 class period each. And you can pick and choose from among these, or you can create about a 1 week-long unit out of this. And the complexity increases as we go from lab 1 to lab 4. All of these are going to be crashable because if you show the crash test videos, your students will want to crash things. The third experiment combines material and shape effects, kind of like what we do in real engineering to minimize weight. We turn all of the knobs we can get our hands on, right, to try to get the minimum weight. And then in the fourth one, we're trying to give students a chance to experience the creativity of engineering and come up with their own beam design based on their experience with the prior experiments. And that one is going to take at least 2 class periods, 1 to make and 1 to break. Okay, so these are those short video clips that I told you about that are on YouTube. And, well, actually, they're available on the ASM website. So if you just wanted to see what we were doing in Lab 1, we started out with simple folded cardstock. So we created a 3-inch wide by 11-inch long rectangle that you can run through your school copier on cardstock and then cut. And the students fold these. So we're contrasting a wider beam shape with shorter legs to a tall beam shape. Okay? And here you can see our setup to test this in 3-point bending. So we're just supporting our folded beam across 2 duct tape rack bricks. We're going to be adding water and measuring how much mass or how much water was added to cause that beam to collapse. The other way that you can test this is just stacking weights on it. Okay? So if you know the mass of a penny, you can stack pennies on these. Okay. I'm going to jump ahead on this one. Okay, so there was our water. So what we found was these tend to collapse by the leg folding under, rather than actually crumpling the center of the beam. And we asked ourselves from an engineering point of view, how realistic is this as a simulation of the B-pillar? Because how often would you be involved in a T-bone crash with both of your doors wide open? There's no support. So we created some ways to support the beams, like both of your doors were closed and latched. And it turns out that it takes a lot more mass to collapse these beams if you keep the legs from folding under. Okay. Laura teaches material science, so she happens to have bags of tin chunks sitting around, so we use those to stack on here. So you can come back and watch that in more detail if you're interested in implementing these in your class. Here's another schematic. So we just folded these. Okay, so you're changing the variables B and H, so we're looking at just shape effects. These two beams will have exactly the same mass because they start out as a 3-inch by 11-inch long rectangle cut out of cardstock. Okay. And here's a close-up of how I supported these when I was prototyping at home. So I had my cookbooks out to support these. It is easier if you get books that are about the same height as your beams. It's just easier to stack things on top if you're not trying to stick them down in between two other supports. And here's our hanging water bottle method. So we stuck an opened up paper clip through our beam, and then to spread that load out and keep the paper clip from pulling out, we put a washer under it. Okay, it's just to keep that wire from pulling out. And here's my cup hanging underneath. So I'm just going to add water or hex nuts or any other source of mass to that. And you can crash test these. This was our prototype. We had a piece of metal hanging from a chain that was supported up top. Okay, we put our beams inside a shoebox that we'd cut some slits into. And we cut away the sides so that we could film this with a cell phone. And I've got a piece of notebook paper back there to look at the final permanent deformation, just like they did in that crash test. Okay. So since we prototyped that, I've modified this a little bit. I hung a bottle of water from a ring stand. Okay, I've cut a different box. This is just an old cardboard box I've cut slits into. I'm clamping my ring stand to the table right here with just some simple bar clamps. So slide your beam into the shoebox. Here I've upgraded to quadrille paper from my notebook paper. But I've also cut away the top, so now I could potentially put a cell phone on top of my ring stand or film, looking down through there, and film this crash test. And you can see that water bottle dropped from a known height will do some damage to these beams. Okay, lab 2. Here we're looking at the effect of different kinds of materials on the stiffness of the beams, on that deflection as a function of applied force curve. Okay, so here I've got a simple white beam. That's styrofoam, and it's been cut out of insulating foam that you can buy at the hardware store. You can cut these with a bandsaw. So I've got that clamped to my table. I'm using a paint stir stick to keep the clamp from crushing this because this is very low density styrofoam and it's not very strong. I'm using that same weight system again. I've opened up a paper clip and shoved it through my beam. I need something to measure the unsupported length off the end of the table, and I want to try to keep that the same from sample to sample because that's a variable in our equation. Okay. And we're going to compare this low-density styrofoam to extruded styrene, polystyrene. It's the same stuff. One is puffy like Rice Krispies, and they're kind of stuck together like a Rice Krispie treat would be. And the other one is extruded, so it's heavier. So we're going to conduct the same kind of experiment. We're going to gradually add water and measure the deflection of the beam. And you can do this in cantilevered, or you can do it in three-point bending. Same idea as before. Okay. So here's our setup in Laura's classroom. We're starting out with a pink styrofoam beam here. And I've got about 1 liter of water, it looks like, in my beaker, and I'm going to use a funnel to put that into our milk jug. Okay. So I'm going to skip ahead here. I'm measuring the unsupported length. Okay. And you would want to have your students incrementally add the water and measure the incremental deflection. And when they plot that, the slope of that plot is going to be related to the stiffness of the beam material. Okay. And if you did this in your classroom, you would probably want a 5-gallon bucket under there to catch your water when things go south. So you can see that's visibly sagged. So that's measurable even in classroom circumstances. I can get the deflection. Let's see if we set up the other way. Okay, so here I'm just changing samples. I'm changing over to my white beam material. So this is pretty easy to change. It'll move along fairly quickly in your class. So I'm just marking where I want that wire to go through so I get the same unsupported length. Okay, I'm going to reclamp it and retest it. All right, let me stop this. Unless we do show you the 3-point bend. I don't remember if we did or not. No. But the 3-point bend works the same. Okay? And you can see this one also creates very visibly sagginess. Okay. So that's how we get at our material effects. And for example, that Rice Krispie-like expanded polystyrene insulation, it has a density of less than half of the expanded polystyrene or the pink stuff, okay? And our stiffness is here, so you can see the stiffness goes up rapidly. One thing that we learned the hard way was if you're cutting samples out of the extruded polystyrene, you'll see almost like a wood grain on the surface of it. It matters whether you cut the samples parallel to the long part of the rectangular sheet of insulation or perpendicular. We gave a work study instructions to get as many beams out of a sheet of polystyrene as we could, and we were seeing big strength or stiffness differences in the two directions. And you'll learn, well, when we learned about polymers and chain alignment the other day when we pulled on our garbage bags, that's what we're seeing going on here. Okay, I'm going to skip this. All right, let's move on to lab number 3. This is the one that I think you're most likely to do at camp this week. So we're, again, starting from simple beams, and you can use that foam insulation if you have some extras cut from your insulation board. You could use dowel rods from the hardware store, or since I didn't have access to a machine shop when I was developing these, I tried uncooked lasagna noodles, and that worked too. So in this lab, students are challenged to apply tape to one surface of the beam, and then measure the influence of that tape on the beam deflection. So you can use the naked beam deflection data from lab 2 to do this one. And to minimize mass, they want to put tape only where it's going to do them the most good. So the winner of this one is going to be who had the lowest value of deflection per gram of beam at a given load. Okay, or who had the best combination of lowest cost and mass, because you could do this with different kinds of tape that have different costs, and they would have to figure out the cost of the tape per centimeter, for instance, and then come up with a total cost impact and look at the payoff that they got for that additional cost. Now, I did make a quick note here. I said apply the tape to the tensile surface. So how do you know what the tensile surface is? If I test this in cantilever bending, where I'm holding onto one end of this with my clamp and I'm applying my load over here, this top surface is going to become convex as that beam sags. The bottom surface will become concave. The convex surface is the tensile surface. It's feeling a tensile stress. We're trying to pull the atoms apart. If you test this in 3-point bending and you support it here and support it here, and you hang the weight from the middle or stack weights on top of it, now the surface that becomes convex is the underside. Okay, so you need to make sure that you put the tape on the surface that is going to be stretched depending on which testing method you decide to use. Okay? So we didn't actually demo this because the testing method is exactly the same, but I wanted to show you some of the beams that we made. This one is my lasagna noodle with duct tape. Here's our cut foam beam with clear packing tape on top. This one is cement with expanded polystyrene mixed in to make it lower density. Here we have one of those folded cardstock beams, and we've used some of the spray-in insulation foam to reinforce it. Okay, I've got a nice way to make spray-in insulation foam composite here with a paper towel holder, paper towel roll, and some duct tape on the bottom to seal it up. So we can spray that insulation foam in there, and now we have a cardboard and polymer composite. So that would be a polymer composite, right? This one is an example of the Lab 4 options. So the students were given the option to vary shape and material. So in this case, a student has taken duct tape and they've attached bamboo skewers to the underside of this lightweight expanded polystyrene bead. Okay, so you guys would rather do than watch. So I'm going to make sure that this stops so it doesn't mess up my recording. Okay, we're going to go on. So here's a close-up of my lasagna noodle. I've clamped it to my table. Okay, my duct tape is on the surface that becomes convex, on the upper surface here because I'm doing a cantilever beam test. Now one of the tricks about this lasagna noodle is the ridges on the side actually do a good job of hanging onto the wire hook for my cup. And in this case I've used hex head nuts as my weight. And I do get a deflection that I can measure. Okay. So let's take a look at how we use this in engineering. This is our same B-pillar sketch that we had before, our exploded view. Okay, so we are only putting the mass where it does us the most good in this B-pillar. So they've put a lot more mass and thickness up here at the top where they do the critical measurement than on the bottom. And we see this again in nature. We saw it in the hollow bird bones, that nature was only putting the material where it would do it the most good. And you see it if you think about a clamshell. The clamshell is really thick where the hinge is, and the shell thickness diminishes as you go out toward the outer rim of the shell. So topological design, putting the material only where we benefit from it, is a big deal for 3D printing. Okay, so if you do the taped lab, the stress scan composite lab, okay, our clamped end is here. This is a finite element model. So it's a computer model of how this part will move when I put a force on it. Okay. My convex side is the top side here, just like we were showing on that lasagna noodle. So the best mass efficient strategy for reinforcing this is to only put the tape up here in this red and orange zone. That's the part of the beam that's really feeling the most effect of that force. Okay. The underside is actually being squeezed, it's being compressed. So as much as the top stretches, the bottom gets the reverse force applied to it, so it's in compression. So it would do me no good at all to put any tape there. Okay, so why did we make the foam-filled cardstock beam? That is reflective of an actual real-life strategy to increase the energy absorption with adding minimal mass. So in this case, they started out with a tube of steel, and they're doing a crush test on it. So they're supporting it on both ends and crushing the middle. And we're measuring how much this is moving, how much it's being displaced as a function of the applied force. So our empty tube has a force displacement curve down here, and our filled tube, just filling it with a polyurethane foam, increases our force displacement curve a lot. So if you think physics, energy is a function of force times distance. So we can think of the area under this curve as representing some relationship to the amount of energy that this would absorb in a crash. So filling this tube with foam increased the energy absorption by 300%. And there's a reading assignment in the package related to the rollover roof crush requirements and how they use the foam filling to help meet those requirements without adding a lot of mass. Okay, so freestyle, lab 4. Here students are free to vary the shape and vary the material to try to come up with the best beam at the lowest mass. So there are a couple ways to test this. You can have a fixed load requirement and figure out who has the lowest value of deflection per gram when you apply that fixed load. Or you could figure out, say I had an allowable deflection limit, who had the lowest cost and mass that met that limit under the specified load. Okay. And here's a real-life example of that. This is another B-pillar, different model car this time. So they've reduced the mass of this by 16% by changing the shape and by changing the material. Okay, so here's our original baseline design. That was made out of a high-strength steel with a certain strength rating. That's what that secret code means. And it was 1.6 millimeters thick. That weighed a little over 4.5 kilograms or a little over 9 pounds. Okay. Here, they've changed the material to a steel with boron in it to make it stronger. They've reduced the thickness by 0.2 millimeters or an eighth, right? And they've brought the mass down significantly. So engineers are actually using this strategy of shape and material selection to reduce mass. Here's some of the samples that Laura Morse students made when we had a chance to do the freestyle lab. This person started with a foam beam, and they cut out the middle of it and added duct tape. Okay, so that should be pretty mass efficient. This student hollowed out the middle of their foam beam again, and then they filled it with the spray foam insulation because that, in their mind, had lower density. But they've also been really sneaky. Down in here, they've got 2 pencils nestled under that spray foam. So that's going to provide tremendous stiffness. This person simply duct taped a piece of PVC pipe to the outside of their beam. So if you think about our finite element model here, where we said the only place that it really does you a lot of good to add tape and add mass and cost is up here in this red and orange zone. They had not seen that picture, but they came up with that same strategy. So if I'm clamping on this end of my beam and applying my force on the right-hand side, this will provide much better reinforcement. It effectively is going to reduce my unsupported length by about half. Okay, so how are we going to test these? I'm going to record that in a separate video and give you a break.